Welcome to our 31st video with data structures and algorithms, and we're going to do an example of Dijkstra's shortest path algorithm. So we need a couple of things. First of all, we need a directed graph, okay, and that has to be weighted, and it has to have non-negative edge weights, okay, for this to work. So we have a couple things. We have a priority queue, right, with distances in them. And we also have an array of parents, and we also have this set of what we're going to put in the set actually is all the nodes that we've already found a shortest path for. So we will do that, and then we have our graph here. So we're going to start from this node here. Start from this here. So what Dijkstra's shortest path algorithm does is it finds the shortest path from some node to all the other nodes in the graph. Okay, so that's from this node where we start to all of the other nodes. We're going to find every shortest path through here. So let's just start. So it's kind of like Prim's algorithm. So first of all, we start at A. So we change its distance to 0, right? It's 0, has a 0 distance away from itself, right? And that is the shortest path so far from A to A, if that makes sense, is 0. And I'm just going to mark this as like it's done, okay? Just a little marker for us. And its parent is nil. So with A, what we're going to do is we're going to check its adjacency list. Okay, so I'm just going to do dotted lines here to show what we're checking. Okay, and we're going to update the keys in our priority queue over here, right? So to B, what we do is we add, right, the distance to A so far, right, the shortest distance to A plus the distance to B. And you'll see that that'll be a little bit more clear as we go along. So that would be 0 plus 5, right? So its distance is now 5. And its parent was A, or we got that from A, right? And then for F, its distance is 0 plus 10, okay, which is 10. So we got that, and the parent was also A. Now, there's no other nodes to check from A. So we go through our priority queue, and we're going to dequeue our shortest one, right, which is right here. So B will be the next one, right, in our set. So I'm going to just highlight that. So B is in here. So just kind of mark this, help us visually. All right, parent was A, so we drew a line, or we highlighted the edge from A to B. Now we're at B. Okay, so let's check the adjacency list of B. Okay, and we'll just make these dotted lines to show that we are just checking these. And we found a path from B to C. So again, here's where we add things, right? So we add the path, right, the shortest path to B, and then add it to the path to C. So it's 1. So it'd be 5 plus 1, which is 6, right? And the parent was B. Do the same thing for F, right? So we have 5 plus 4, okay, which is 9. 9 is less than 10, so we'll definitely update that. And we have a new parent here, which is B. So that's all there is, right? There's no other nodes in the adjacency list. So we're going to take the smallest value in here, right? We have a priority queue, so the next one up is C. So C is finished. We found the shortest path from A to C now. And we will highlight this. Okay, like that. Okay, so now we're at C. So let's just keep going with our algorithm. We'll check its adjacency list. And we'll update our priority queue, right? The keys in our priority queue. So to D, a path to D from A, so far should be 5 plus 1 plus 6, right, which is 12. So let's do 12 and C, right? C is the parent. And then E, we have 5 plus 1 plus 2, right? Which is, let's go back down here, 8. And there it is. And now there's nothing left to check. So we grab the smallest value in here, which is E, right? E is up next. So E goes into here. And let's highlight this. Okay, there we go. Now we're at E, right? So let's check its adjacency list. Okay, now we have another path to D. So let's see how long this path is. We've got 5, 6, 7, 8, 9, 10, 11. So we've got 11 here. 11 is less than 12, so we found a shorter path. Let's update that. And we got that through E. Okay, and then for F, what do we have? We have 5, 6, 7, 8, and 9. Now, 9 is the same here. So we have two paths that are not, right, that are a distance of 9 away from A to F. So in our algorithm, we're just going to leave it. Okay, we don't really need to update it. It doesn't matter. It just depends on what your actual algorithm does. So we'll just leave it in this case. Either way, it's the same distance away. So we'll just keep it. There. So now we'll take the lower of the two, right? The lower of the two values that are left in our queue, and we'll add it. And that happened to be 9, and its parent is B, right? So let's just highlight this one. Okay, there we go. So now F, right? We found a shortest path to F, and we're done with that one. So let's check the adjacency list of F, right? And we see that B and C, right, both of them are already, we already have found a shortest path to them. So there can't be any shorter path, right, to those two nodes. So we don't do anything. Now we have our last node, right? That's in the adjacency list, or I mean the priority queue, sorry. And its parent is E, right? So we will highlight this. Okay, and now D. We found a shortest path to D. And that's it. That's all of our nodes. So I'm just going to highlight this a little bit, right, with yellow. So we have found a shortest path from A to every node in our graph with Dijkstra's shortest path algorithm. And here you can see I've just highlighted it with yellow, right? So there is no shorter path to any other node, all right, along these edges that we did not highlight. So that's it.